edition of lecture chemistry on the platform of ScoreBooster, and the topic we are going to treat today is chemical reactions. A very important topic as usual, and it's going to be presented by our regular chemistry tutor, which is Sahid Adewale. So after today's class, it is our expectation that students should be well acquainted with some concepts about chemical reactions, such as what is called chemical reaction, then the rate of chemical reaction, how to define it, what is the significance of rate of chemical reaction, what is the motive behind taking this topic. We should be able to explain the concept of the theories as applied to rate of chemical reaction, because there are some theories that are very useful under this concept. So after this lecture, it is expected that students should be able to explain all those theories and apply them in explaining what is called the rate of chemical reaction. And apart from that, there are some factors that affect the rate of chemical reactions, such as temperature, concentration, catalyst, as we are going to see. So we expect students to be able to identify these factors and how do they affect the reaction, to what extent, how is it positively or negatively. If you want them to affect the reaction positively, how do we do that? Then again, determine the types of catalysts for various chemical reactions and their effect. As I've said earlier, catalysts it's also a very big factor that affect the rate of chemical reaction. But how do they do that? That is what we are going to find out today. That is among what we are going to find out today. Just sit back and enjoy it. So the picture we are seeing is just a pictorial representation of 4 different reactions. The first one is the ripening of fruit. This is apple. It's ripening of fruit, and if we have been familiar with what happens during ripening of fruit, you can see that it takes place more than some days. The reaction, if we assume, if you take ripening of food as a reaction, it takes days. And this is making of cheese. As I have seen, this is cheese maker, this is cheese. So for this to be able, as in to ripe, for further processing, so as to be able to be edible, so it takes some weeks. And this is coal. Yeah, maybe someone is making fire with the aid of coal to be able to use for baking bread or some other things like that. It takes some minutes for that to be done, and this is something like an explosion that takes seconds. As we have seen, this each of these 4 represent different reactions, and they are faster than each other, which means they are more complex than each other. So if we take that at the back of our mind and apply that in a chemical industry, we are going to see that some reactions are actually more complex than the other. So if we are dealing with a complex reactions, so we expect that this will take place faster than each other. So that will bring us to the concept of what is called the rate of chemical reaction. If particular reaction takes place at a faster rate, what does it mean? If it takes place at a smaller rate, what does it mean? Then how can we manipulate, how can we maneuver the reactions such that we can actually improve the rate, as the case may be, or reduce the rate? It depends on what you are looking for, as we are going to see later. So rate is an English word, is having from English language and mathematics. We know anything that is that has to do with time is called the rate. So the rate is a measure of the change that happens in a single unit of time. If, as of now, that we want to know how fast a person is, so we can actually calculate the distance the person has traveled or the object has traveled, then we consider the time at which it takes to reach that distance. That is an idea of what is called a rate. If somebody is reading a particular book, now let's say a novel has maybe like 100 pages. Somebody takes 10 minutes, somebody takes 10 hours to read that. I think they are faster than each other. That is the idea of what is called the rate. So if you have a particular span of work, so the time it takes to finish that work, if you consider that work and the time it takes, that is called the rate. So the same thing happens in the chemical reaction. If you have A and B that react, the time it takes for product to be formed is called the rate of chemical reactions. So any suitable unit of time can be used depending on what we are considering. It could be a second, it could be a minute, it could be an hour, even we can use a year if that reaction is not what takes place instantaneously. Example of this a zinc reacting with H2SO4 to form zinc sulfate and hydrogen. So if we want to determine the rate of this reaction now, a solid reacting with something in aqueous solution to form another solid in aqueous solution, then plus gas. How do we know if a chemical reaction has taken place? The first thing we do is we look at the color change. That is in the laboratory. If you want to know if a reaction has taken place, the first thing we do is to check color change. If there is a change in color, then a reaction has taken place. Another thing is difference in weight. You weigh the reactant before the reaction, then when the reaction is going on, you weigh them. Maybe there's a change in mass from the start of the reaction to the end to some particular time during the course of the reaction or the end of the reaction. That would tell us a reaction has taken place. And again, if something involves evolution of a gas, so definitely we expect the volume change when the reaction has taken place. So the volume change is also another factor, another parameter that is used to ascertain that a reaction has taken place. So in this case now, both zinc and sulfuric acid get used up in that reaction, and at the same time as zinc and H2SO4 are getting reduced in the reaction, there is formation of zinc sulfate and hydrogen in gaseous form. That is the simple explanation of what the rate of chemical reaction is. So in general, if you want to find the rate of reaction, you can't find everything at the same time. To make it convertible, out of the three parameters that I said color change, change in mass, and change in volume of any element of any part of the constituent of that reaction, say the reactant or the product, depending on what you are looking for. If a reactant is colored, one of the reactant is colored and that color is disappearing, so a change has taken place. Or reactant is not colored and suddenly one of the products, we expect them to be a colored substance, then you see that color change, that product change to that color, then a change is taking place, reaction is taking place. Or you see one of the products is a gas, it is evolution of a gas, so we expect volume increase of that gas. So that is another evidence of the reaction has taken place. So the amount of reactant used up per unit time, as I've said earlier, it depends on what you can measure. A measurable quantity is what you use, or what something you can observe. Then the amount of product that are formed per unit time. So that is the idea of what is called the rate of chemical reaction. So to be on the safer side and to be fair to the results you are getting, make sure the time you are using is constant. If you are using seconds, let's say 1 second. So use interval of 1 second. If you're using 10 seconds, if it's reacting that can take that spend time to completion, so you can use 5 seconds. But it's such a way that the first reading you take it after 5 seconds, you take the second one after about 6 seconds, then that means you are not being consistent. You have to make sure the span of time you are using is the same, so as to give us the idea of what is called the rate of chemical reaction in true sense of it. So one of the theories that is used in explaining the rate of chemical reaction is correlation theory. What does it mean? What are we trying to say if we say that we are using correlation theory to explain what chemical reaction is? Correlation theory states that for a chemical reaction to occur, then the particles must collide with one another. That is the first thing, the first idea about correlation theory. The particles must collide. And if you can remember, when we were discussing kinetic theory, one of the postulates in kinetic theory is that every matter, irrespective of the state of which that matter belongs, contains molecules which are in constant motion, colliding with one another and with the walls of the container. So if you now have two or more substances in a particular system reacting together, so the first thing is the molecules must collide with one another, so when they are moving at random in that container. So now, if molecules are colliding, that one has not given us any information that a chemical reaction is going to take place. Now let's now go to the second point. So for products to be formed, then the coalition has to have a certain minimum amount of energy associated with it. What are we trying to say with this point? We have said that there must be coalition. Then, before the coalition will now lead to chemical reaction, we should not forget from kinetic theory that there is force of attraction among the molecules. So now, if you have a molecule A and molecule B reacting together, you want A and B to react to form C and D, or to form C, or to form anything. It means that the molecular forces holding the molecules of A together, the molecular forces holding the molecules of B together, something must break them, so that molecules of A will be free to react with molecules of B. Another molecules of A will be free to molecules of B, so as to form another product. So this coalition, that means this coalition must have energy which are greater than the forces of attraction among the individual molecules of A than that of B. What I'm trying to say is that the adhesive force must be greater than the cohesive force among A or among B. The adhesive force between A and B must be greater than the cohesive force between A molecules and B molecules. So that minimum amount of energy all these molecules have is called what is called kinetic energy, EA. Activation energy, EA. So any time that this coalition has energy more than this activation energy, then the reactant cross to the product side. If the energy of the molecules is not up to that activation energy, then the reaction is still on the reactant side. That is what is called coalition theory. From this pictorial diagram now, this is the reactant side, this is the product side. This point is the minimum amount of energy that the reactant must possess to form product. So if we have reactant here and the amount of energy they have is at this, they can't form product because this is the energy that they must have. That is the minimum amount of energy. Let's say this is 50 joule now, and here is around, let's say, 30 joule. So for that molecules those molecules to form a product, they must have more than what is required here. If they have 30 joules, that means they can't cross to this reaction. If they have 42, 43, 45, up to 50. So this particular 50 is the minimum amount of energy they have. So at that 50 is what is called activation complex. At that 50, don't be confused, I'm just using 50 as an example. So at that 50, they have what is called intermediate. They are not reactants at that point, and they are not product. So any moment that they have more than 50, then they cross the product side. That is what we are saying. So it now depends on the energy, the nature of the reaction. If it is exothermic or endothermic, that will determine the amount of energy reactant or product have, which one is more than the other. So the overall energy change is different between the energy of the reactant and the product, which can be positive or negative. We're still coming to that. And this is the activation energy, and as I think I've explained, that this is the energy and this is the progress of reaction. It may be time in hour or in seconds or in days. So now, these are the factors affecting the rate of chemical reaction. The first one is the surface area of the reactant. All of them are important, so it is immaterial whether I take the concentration as the first one, or the temperature as the first one, or surface area of the reactant as the first one. So just know that each of these 5 properties, 5 factors, 5 parameters are the factors that affect the rate of chemical reaction. So let's just start taking them one after the other and see how we can use our collision theory to explain what we mean by all those and how they affect chemical reactions. So the first one is the surface area of the reactant. What is called surface area? Surface area is the area accessible by another reactant. Let us assume that we have a solid reacting with a liquid. So liquid will be getting into contact with that solid. What area of that solid can the liquid get in contact with it? If you have small molecules, are they going to is there going to be contact faster than when we have a very big lump? Can the molecule enter inside faster than when we have small molecule? That is what is called surface area. Surface area is the area accessible. So if you consider this reaction between limestone and hydrochloric acid to form calcium chloride, CO2 and water. So this is the pictorial representation. This is the first and this is the second. In this case, we have the lump form of calcium carbonate. This is limestone. Here we have the powder form. They have grounded the lump form into small particles, and this is it remains a big solid particles. So when these HCl now come into contact with each of them at the same time, so we try to measure the area, the extent to which reaction has gone. Don't forget, we said the loss of mass is one of the parameters that we use to measure that the reaction has taken place. This is calcium carbonate. If you have the mass of this, you add this to the mass of this initially. So at every stage of a reaction, let's say now, like here now, we use time in minutes, 1 minute, 2 minutes. After 7 minutes, then the reaction now goes to completion. So what happens? Because we are using loss in mass in grams, it is because we have a gas as our product. So the gas can easily escape from the mouth of these test tubes. So when the CO2 now escapes, so we have only water and calcium chloride, which I think we can easily measure their mass. Then differential in the mass tells us that reaction has taken place. So now after this reaction, this is just a hypothetical reaction. After this reaction, they have plotted the loss of mass against the time it takes. So we have seen this curve and this curve. The steeper the curve, the higher the rate of the reaction, which means the lump form has a steeper. If you find the slope of this is the rate of reaction, that is the loss in mass over time. So you can see this slope is steep, so we get higher value for the slope than in this case. So a powdered limestone has a higher rate of reaction. The surface area is higher, then the rate of reaction is higher than when you have lumps of limestone. In this case, we say that the surface area is proved to have influence on the rate of chemical reaction. Another one is the concentration of the reactant. In this case, definitely concentration is the amount of solid in solvent. The amount of solid in solvent, that is concentration. How much quantity of a solid that is dissolved in a solvent. So a yellow precipitate is produced in the reaction between sodium thiosulfate and hydrochloric acid. Sodium thiosulfate is a liquid solution. Hydrogen chloride is also a liquid solution. In this case, we have color change as our indicator. Color change of sulfur here as our indicator. So in order to know to study this rate of reaction here, we put a white paper whose X is drawn on top of it. We now put our reaction flask on top, so that as the color is changing, the X will not be visible again, to be gradually disappearing. So at a particular time, we are not going to see the X again. That is what we are seeing here. This is the start of the reaction. We have seen the X clearly. Then later X will be fading away. We will not be able to see the X again as the reaction is proceeding. So as we are doing that, we are measuring the time. So we now plot the time for the cross to disappear against the concentration. So that is what we're saying. We repeat the experiment using different concentrations of any one of them. Any one of the reactants. It could be this or it could be this. Any one of them. So this is what we have. We are seeing that this is this very small concentration. This is a very big time. So when you have a very big time, then that means you have very small rate, because the rate is the inverse of reaction time. What I'm saying is this is at 0.015. You have 80 seconds. So if you flip that, 1/80, you get a particular value. So when you now have a small time around 30 at very big concentration, what is the rate? You are going to see that you have higher value here than higher value here, because the big time here, it means a small rate. If you flip it, because it's going to be inverse, rate is inverse of reaction time. In order to appreciate this, because I think this graph might be confusing, in order to appreciate that, we have another plot here, the same reaction. So instead of this time, we are now plotting the rate against the same concentration. So we just flip this 1/20, 0.00540, 0.01, like that, up till this point. So now at small concentration, we have small rate. At higher concentration, we have higher rate. I think this one is simpler to explain than this. So in this result now prove to us that the concentration affect the rate of chemical reaction. If you have more concentration of any of the reactant, you have a faster rate of reaction. How can we explain this in terms of collision theory? higher concentration means higher molecules, more molecules to get into contact with one another. So when you have more molecules, then you have higher probability than that the coalition will be effective, that the coalition will lead to formation of a product, than when you have small molecules. I am not saying if you have one molecule, the reaction is not going to take place, or if you have 3 molecules, all the 3 must lead to formation of product. What I'm saying is, if you have more molecules, you have a better probability that the coalition will lead to formation of product, and that is what we are explaining in terms of concentration. Another one is temperature. Again, from kinetic theory, temperature increases the reactant particles. If temperature increases the rate at which the particles move, then the coalition will be more vigorous than at lower temperature. That is the first one. If the coalition is more vigorous at higher temperature, then we have a very high probability that more coalition will lead to formation of products. That is in terms of coalition theory. So we have put kinetic theory and coalition theory together here. Kinetic theory, don't forget the postulate 5 of kinetic theory, which says temperature is a function of kinetic energy of the molecules. So the more the temperature, the more the kinetic energy of the molecules. So now if you want to increase the kinetic energy of the molecules, you increase the temperature. If you increase the kinetic energy of the molecules, they move faster. If they move faster, they collide more. If they collide more, you increase the probability that coalition will be more effective. That is what leads to increase in the rate of chemical reaction as temperature increases. So this plot gives us the idea of that. This is another experiment done, and this is the result. So time for cross to disappear, seems like we have this reaction now. So instead of concentration now, so we are now using temperature. So at 20 degrees, this is the time. At 60 degrees is the time. And don't forget again, if you flip this time, you get rate. So higher time means lower rate, then lower time means higher rate. So at this point, we have higher reaction, because at 60 degrees the cross disappears faster than at 20 degrees Celsius. So at 60 degrees Celsius, it took the cross to disappear. It took it 20 seconds. So at 20 degrees, it took it 6 seconds, around 130 seconds. So which one is faster? I think it's 20. That is the rate that we're talking about. So now another point is the light intensity. There are some chemical reactions that are influenced by light. So when those particles now absorb the light, then don't forget that before a reaction can take place, there must be breaking and forming of bond. So when particles now absorb light, that light energy breaks the bond between the particles, overcoming the kinetic energy. Then the reaction now takes place. Example of that reaction is photosynthesis, where the energy of the sun now breaks the water into hydrogen and hydroxy. Hydroxy goes into the body of the plant, reacting with the glucose inside. Reacting with carbon dioxide inside to form glucose. That's as food that we eat. Another reaction that is light sensitive is the reaction of the photographic film. That film is made of silver compound, a very complex compound of silver. So that compound, if it's exposed to sunlight, is going to break it and destroy the film. That is why, remember, they used to warn us that time that films are not, we should not allow the film to get in contact with the outside, and it is because of the effect of light. So the light will destroy the silver compound on the film. So examples of reactions like that are photochemical reactions, and I've given you 2 examples. So light is also part of the parameters that affect the rate of chemical reaction. So the more the light, the faster those compounds break. So another important one is the catalyst. In industry, whether it is petrochemical industry or chemical industry or any type of industry where chemical reactions are taking place, even not chemical reactions, that some biochemical reactions also depend on catalyst. So these catalysts are substances that are used to speed up the rate of chemical reaction. Speed up means you increase the rate. If you increase the rate, you want a complex reaction to happen at a particular small span of time. What are we trying to say? That you want a catalyst, a substance, a reaction that ordinarily supposed to take place in 5 hours. So you want them to, you want it to take place in 2.5 hours or in 1 hour. That is the effect of catalyst. What can catalyst do? Catalyst lowers the activation energy, so it makes the energy that molecules have, it makes it easily to, it makes that energy that the molecules have, it makes it very easy to overcome the kinetic energy, activation energy, because the catalyst has reduced the activation energy of the molecules. So that means it has affected the rate of chemical reaction. So one thing about this catalyst is that small amount of catalyst is needed to effect the change. That is number 1. The number 2 is it remains unchanged chemically. Although the color might change, the physical structure might change, but chemically they remain unchanged. After the reaction, you take back your catalyst, and if it's possible to regenerate it, then you regenerate it and use it for another reaction. So this reaction that we use, if you want to break this hydrogen peroxide into water and oxygen, vanadium manganese peroxide is used to break this faster than when you don't have catalyst. And again, catalysts are specific to a particular chemical reaction. So example is in photosynthesis that we have sunlight as a catalyst. In organic reaction, when chlorination of methane, so it uses UV light. If we assume UV light is a catalyst, but more appropriately we should have explained the effect of UV light under light intensity. So Haber process, that is when hydrogen reacts with nitrogen to form ammonia. So iron is a very good catalyst. Then hydrogenation, cracking reaction, and lots of reactions like that takes place in petrochemical industry. We use nickel, we use platinum. In contact process, when we have manufacturing of sulfuric acid, we use vanadium oxide. Then there are some reaction that involves oxygen, like oxidation reaction. If you have oxidation of propane, oxidation of some organic substances, we use also vanadium oxide. So this is how a catalyst affect the rate of chemical reactions. Pictorially, this is what we have. If we don't have a catalyst, this is the activation energy. If we now have a catalyst, this is the activation energy. We can see if this is the energy of the reactant. If we don't have a catalyst, the reactant has to overcome this huge amount of energy for product to form. So when we now have a catalyst has successfully drag that activation energy down from here to small. So the energy that reactant need to form product is not much again, so it has increased our probability, our chance of having a successful reaction. So in catalysis, catalysts are used especially in catalytic converter in cars. This is the reaction that takes place in cars. So without catalyst, you can have this CO that will not be able to catch up with oxygen. So this many CO will be escaped into the atmosphere and cause air pollution. But with catalyst, this reaction can take place faster. So the remaining CO will react with NO, and we have CO2. If CO2 can be released into the atmosphere and nothing will happen, plants will need them, then this is a diluent in the atmosphere, as I've explained it under here, a mixture of gases. So what catalyst is doing here is to make this oxygen react faster with this CO. Because it's inside, we have very small amount of oxygen. So if some CO are reacting with this NO, so the other ones, the excess CO that is from the internal combustion engine, if they don't meet with oxygen, they will be released into the atmosphere. Instead of reacting to form, this reaction will not form. CO will just be ordinarily released into the atmosphere through the exhaust of the cars. That is air pollution. So with catalyst, we have, as this one is taking place, this one is also taking place. So we have CO2 that is being released into the atmosphere. So catalyst speeds this rate of reaction, and that is what we have for today. So before we go, let us have a quick recap of what we have said. A rate of chemical reaction is a measure of the amount of reactant used up or product formed in a chemical reaction. That is the first point that we discussed. The second point is the formation of products is a function of the number of successful collision and the energy of the reactant. The energy of the reactant brings about the number of collision. The number of collision brings off the idea of the successful collision. So if you have 1 million collision and you have 10 collisions, I think probability of getting successful collision in 1 million collision is far more than when you have 10 collisions. That's what we are saying. The second point here, there are some factors which affect the rate of reaction, such as temperature, surface area, concentration of pressure, or pressure in the case of gases. If you have liquid, we talk about concentration. If you have gases, we talk about pressure. So catalysts offer an alternative pathway to lower the activation energy of the reactant. Yes, that is what we are saying. By catalyst, it reduces the activation energy, making the energy of the reactant to be able to be enough to overcome the binding energy that is holding the molecules together, which should ordinarily prevent the formation of product. So when you now have the catalyst, it will lower the energy, and the energy of the reactants will now be able to surmount that force that should ordinarily prevent the reaction from taking place. So before we go, let us have some exercises to test what we have understood. Although we can't take everything, but the little one we have taken, let us make sure we understand the concept we've talked about. Which of the following best explain the increase in the rate of chemical reaction as the temperature rises? So when you have increase in temperature, what is the main point? That we said increased temperature increases the rate of reaction. We said increase in temperature increases the collision. I mean, it makes collision more vigorous, so the number of collision increases. So when you have the number of collision that increase, you have a probability of getting reaction. So it increases the rate of reaction. So that's option D. A chemical reaction is always associated with what? A change in nature of the reactant. B, formation of new substances. C, a change in volume of the reactant. D, an increase in the composition of the substances. This question is simpler than the first question, because this is just ordinary SS1 question. In the chemical reaction, something must take place. There must be formation of new substance. If there's no formation of new substance, we have not had chemical reaction. So now all other things that is mentioned here, I mean option A, option C, and option D, they are just indicators of as in the indication of chemical reaction, the happening of a chemical reaction. If you have a change in nature of reactants, then that means a chemical reaction has taken place. But not necessarily that the nature of the reactant must change before we can say that a chemical reaction has taken place. Another one is the change in the volume of reactant, as I've explained earlier. It is not every time that we expect a change in volume. An increase in the decomposition of one of the substances, this is not part of it. So the correct answer here is the formation of new substances. This is B. Another one, which of the following will change when a catalyst is added to a chemical reaction? I just explained that the catalyst lowers something. So go and find out that one yourself. And the last one that we're going to take today is primary 2 question. In the diagram above, the respective activation energy of the catalyzed and non-catalyzed reaction in kilojoules are this. Just this is the energy of the reaction. So what is the activation energy? This is the uppermost point of each of the curves. For the catalyzed and non-catalyzed one, just trace each of these points. You trace it to this vertical axis, and you determine that from your readings. So with that, we have come to the end of our discussion on the rate of chemical reactions. I believe we have understood a little concept in the little way I've explained it. If there is anything that is not clear, feel free to ask us at www.scoreboosterproject.com, or you write it as a comment under our videos. And if there is anything you want us to change or adjust in our lectures, feel free to get back to us. God bless you really good for listening to our videos and for following us in all our courses, the chemistry, mathematics, physics, and economics. So more are still coming by the grace of God. So expect our next video to be on chemical energetics, and as usual, we are going to have some sample questions and solutions. Thank you very much as you are listening. Please don't forget to subscribe to our YouTube channel, like and share our videos.